So a reminder, the rate law must be determined experimentally. Graphing is the most straightforward way to do that. So we can graph concentration of a reactant versus time and use that to determine the effect of concentration. In order to solve these, it involves calculus beyond the scope of this course, but we can look at the results of the calculus and determine what types of graphs to make to tell if a reaction is zero, first, or second order. What we're going to use for that is called the integrated rate laws. So for a general reaction, A goes to products. The rate law is going to depend on the concentration of A. And if we apply calculus, we can integrate the rate law and get the integrated rate laws. Here they are. So for a reaction that is zero order, the integrated rate law is that the concentration of A at a specific time is negative K, the rate constant, times the time, plus the initial concentration. So all of these integrated rate laws are in the form of Y equals mx plus b. So if I graph that, I get a slope of minus K and a y-intercept of my initial concentration. And then we can also calculate half-lives. A half-life is the amount of time that it takes for half of the material to go to products. And so you can see that the half-life here is dependent on both the rate constant and the initial concentration. For a first order rate, the integrated rate law involves natural logs. So the natural log of the concentration at a time is negative kT plus the natural log of the initial concentration. If I graph that, my slope is negative K, my y-intercept is the natural log of my initial concentration. For the half-life of a first order reaction is not dependent on the initial concentration. It has a consistent half-life, and that half-life is 0.693 divided by K. For a second order reaction, if you want to have the integrated rate law in linear form, it's 1 over the concentration at a specific time is kT plus 1 over the initial concentration. Here we get a line where its slope is positive K, y-intercept is there at 1 over the initial concentration. And again, we have a half-life expression where the half-life is dependent on both the rate constant and the initial concentration. So this table is in your textbook. It's table 13.2. You'll probably be referencing it several times. You will always be given the integrated rate laws on a test. Now I have slides that go over the highlights of what I just talked about. So a zero order reaction, the integrated rate law is just the concentration is negative kT plus the initial concentration. So there's your straight line. For a first order reaction, the half-life is constant. So it doesn't matter how much material you have, that half-life time is the same. And that's true only of first order reactions. Zero order, second order, they do not have consistent half-lives. Okay, let's work through a problem using our integrated rate laws. The reaction given there is first order with a rate constant of 2.9 times 10 to the minus 4th per second at a given set of conditions. Find the concentration of that reactant at 865 seconds when the initial concentration is 0.0225 molar. And we have the integrated rate law here. So really all we have to do is plug things in. So we want to find our concentration at a certain time. So the natural log of our SO2Cl2 is equal to K. This is negative K. Sorry, there's a typo on my slide. Negative, my K value is 2.90 times 10 to the minus fourth times my time, 865 seconds. This is per second, this is in seconds, so that's good. Plus the natural log of my initial concentration, which is 0.0225 molar. So my natural log of my concentration at the time I want is equal to negative 4.045. And then if I take E to the natural log, that's going to get me E to the negative 4.045. So then my concentration is equal to 1.75 times 10 to the minus 2 molar. And just a reminder that E to the whatever button is the shift of your natural log key. And you can make sure that this makes sense because we're starting at 0.0225 molar. Now we're at 0.0175. This molar. This is less than this, so it makes some sense. Here's our rate law table again for reference, probably for our next question. Molecular iodine dissociates at 625 Kelvin with a first order rate constant of 0.271 per second. What is the half-life of this reaction? So for a first order process, our half-life is only dependent on the rate constant. And this natural log of 2 is the 0.693 from the previous slide divided by K. So our half-life is going to be 0.693, or the natural log of 2 divided by 0.271. And that gets us 2.56 seconds.